Simplest way of looking at this is, say we are in a synthetic mode, a biosynthetic mode in the cell, and we are synthesizing nucleotides. So we're in a biosynthetic mode, so we need NADPH. We're synthesizing nucleotides, so we need the ribose 5-phosphate. I don't know why it did that on the slide. Right? Automatic respacing of a font change or something. So, we start with one glucose 6-phosphate, we oxidize it, we open it up, we oxidize it again. So we've made 2 NADPHs for biosynthesis. Now we've got, when we decarboxylate that, we get a 5-carbon sugar, ribulose 5-phosphate. We convert that to ribose 5-phosphate. We use the ribose 5-phosphate in nucleotide synthesis. A nice direct line. And that carbon is not getting back into gluconeogenesis. It's being used to synthesize other things. Right? That's the most straightforward layout of the pentose phosphate pathway. And these are available online, right? Those are available on ACE. Okay? Now, what if we just want to produce ribose phosphates, which is possible? If you just start with glucose 6-phosphate, you can make fructose 6-phosphate. And I think there should be a 5th arrow here, right? Because the arrows designate how many times we're doing it. So if you have this figure, add a 5th arrow there. But do it in pencil in case I realize I messed it up. Okay. So you got a 5th arrow there. So from glucose 6-phosphate, we can make fructose 6-phosphate. We can use phosphofructokinase to make fructose 1,6-bisphosphate. Aldolase to make dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. The triose phosphate isomerase to convert this dihydroxyacetone phosphate into a second glyceraldehyde 3-phosphate. We can do transketolase twice to take 2 of the fructose 6-phosphates and those 2 glyceraldehyde 3-phosphates to xylulose 5-phosphate and erythrose 4-phosphate. We can take the 2 erythrose 4-phosphates and the other 2 fructose 6-phosphates with transaldolase to make glyceraldehyde 3-phosphate and acetoheptulose 7-phosphate. 5-carbon, 5-carbon, 5-carbon. We can equilibrate those and end up with 1, 2, 3, 4. Should be 2 and 2. There should be 2 more arrows there. 6, right? We can take 5 glucose 6-phosphates and make 6 ribose 5-phosphates out of it. So add 2 more arrows right there. And you're good.
Where does the other product come from?
5 of these. Remember I said to add an arrow there.
Sorry.
5 of those to make 6 of those. Now, just to throw another possibility in the works, I don't want to say wrench. I was trying to avoid saying wrench. Remember, we eat things that contain ribose 5-phosphate, right? Don't we eat biological products? Don't those biological products have RNA in them and have ATP and GTP and UTP, right? We eat things that when they're metabolized release ribose 5-phosphates. So if we're talking about the metabolism of ribose 5-phosphates that we get from our diet, it would be the reverse of this. That is, 4 here, 2 here. All of these reactions are equilibrium reactions, or at least are reversible. We would have to go the alternate route around here like gluconeogenesis. But still, we can take these 5-carbon phosphates that we get in our diet and take them back to glucose 6-phosphate by just reversing this pathway. What's the matter, Michelle? You got a funny look on your face.
I feel like I can't like get anything to stick with me today.
That's okay. You're distracted because you didn't get to take your test this morning. Okay, so if we just want to produce NADPH and get all the carbon back into glycolysis or gluconeogenesis, it's essentially what we've been talking about. 6 glucoses, oxidized twice, losing 6 carbon dioxide, leaving 30 carbons in this pool, right? Reorganizing those to 2 xylulose, 2 ribose, and 2 more xylulose. Xylulose and ribose with transketolase, making 3 and 7. 2 5s make 3 and 7. 3 and 7 make 6 and 4. 4 and 5 make 6 and 3. 2 3s make 6. 6. We have 2 6s there and 2 6s there.
Why do we sometimes start with 5 glucose 6 phosphates and sometimes we're starting with 6?
Depends on what stoichiometry we need to accomplish.
Okay.
Right, in one, I only wanted to, it's a least common multiple issue.
Okay.
If I want to end up in 5 carbon, when we start with 5 glucoses was when we wanted to make ribose, right? And ribose is 5, and the least common multiple of 6 and 5 is 30. So I needed 30 carbons for those to be equivalent. Right. One more. If we want to produce NADPH and ATP, instead of going through gluconeogenesis, we take all of these things that go back to glycolysis, we go down glycolysis, and we make ATP out of it. And so there's a layout that way. So that finishes my modes of pentose phosphate pathway. Next, we'll talk about some specific reasons why we need to do the pentose phosphate pathway. But that now should open up, we should be ready to start glycogen metabolism on Wednesday. Correct?
Sure.
Okay.